right. It works. Yay. Right. Light is that? Oh, no. Nope. None of these? Oh, that's good. Yeah. Over here. All right. As a reminder, right, homework is due today for those who are online. Surprisingly, not very many today. I know we got a few more people in class, but not quite proportionate to the number online. But maybe those people are doing their homework right now. Who knows? Right. But if you're online, you should be able to submit it online. If you email me about it, unless I forgot to add you to the list of students who can, in which case I apologize. And if you can't submit it online, just send me your homework via email, and I'll still grade it there or whatever, and let me know that, hey, you couldn't submit it online. But otherwise, you should be able to submit it online by the end of class. Okay? Yeah, surprisingly, much fewer people online compared to. Yeah, whatever. So before we get going today, so I have some more information. So they have found a replacement for me. The new professor will be teaching this course. Her name is Kelly. I forget her last name off the top of my head. I'll be having some conversations with her on Thursday. I've been communicating a little bit over email right now. But what it sounds like, at least kind of asked her, is she plans on doing the course completely online, but synchronously. So basically the same, so right, lectures at normal 11 to 12:20 and things like that. But there will be but she won't be here in person, right? So you'll basically be on Zoom for all the lectures, is what it sounds like she'll be doing. Okay. And as I said, I think that was going to be kind of potentially the biggest change, just because, again, right, everyone's comfort level with things is different right now. Obviously, right, at least like half the class is wanting to take this class online. For whatever reason it may be, maybe because they're not comfortable coming in person or not. But yeah, so that change will happen. But otherwise, I mean, through a conversation with her, I don't think she's planning on making any other kind of significant changes, right, since the semester is kind of going and everything else like that, right? But that will be, I guess, the biggest change is that the course will be fully online. That will start next week. So still working things out in terms of when exactly she's starting and things like that. So I will kind of let you guys know more by Friday when I know more of some things and in class, and I'll also send out some announcements and things like that on Canvas. But yeah, starting next week, there will be no more in-person meetings. Okay. And things will things will just be online. Now, yeah, there's some little break between potentially when she's able to start and when I need to finish. So hopefully she's able to start by Monday next week. Otherwise, I will still kind of be in charge of the class next week, but I won't be able to do like a regular Zoom meeting at normal class time, at least on Monday. And so it might be that next week I hold kind of a class office hours aside some time of the regular class time when I'm able to. But otherwise, I'll at least be uploading. So I already uploaded lecture videos for next week as normal. But I might upload some extra videos of doing example problems and things like that. You know, the thing is we are kind of ahead of schedule right now. So my plan is, you know, to kind of continue as things are. And if, you know, next week there's a little bit of a slowdown in terms of the schedule and things like that, it won't be that big of a deal. Since, you know, if we're like on the current pace right now that we're on, we'll, you know, finish easily everything with kinetics by sometime next week. So yeah, that's kind of the state of things. Like I said, I'll be talking tomorrow in a Zoom call with the new faculty about things some more, and can give you guys potentially more updates on Friday in terms of any changes to expect, and then what is happening next week and things like that. Yeah. So I apologize, you know, about the, you know, this kind of change up at the, you know, in the semester, right, as things are starting to get going and whatnot. But yeah. So, questions? Yep.
So like, what is our exam gonna look like? That's confusing. Are you making that, or is she making that?
I mean, so I'm going to be giving her all of my old exams. Like I have exams from like the past 3 or 4 years that I've taught this course. And I'll talk to her a little bit about that tomorrow if she wants me, since it's kind of, you know, the start, just to like give her a version of the exam that I would be doing for this year. And she'll use that. So I'll talk to her a little bit about that tomorrow in terms of the next exam. But yeah, so I'll be able to answer a little bit better on Friday after I talk to her as to whether or not she plans on just kind of keeping the same exam format that I have been doing, or if she will do maybe some more short answer questions or conceptual questions or other things like that. But yeah, that's a good question, and that's something I'll kind of talk to her about, just so you guys have a better idea of what to prepare for, especially for this first exam. So. Other questions, comments, concerns? Anyone here? I think I'm hiding the thing from chat. Oh yeah, there's all sorts of crap going on in chat. Sorry. Okay, will she be posting her lectures, Daniel? So I don't know the answer to that question yet. Again, I've mainly passed her along some of my information and all the course material that I have, and told her about how I have been doing things, you know, and then asked her about whether or not she'll be teaching kind of hybrid like I've been doing, or online, or things like that. And so she told me that she'll be doing things only online. But again, synchronously, again, meaning that, so it's not going to be something where she just posts some videos, you kind of watch them at your leisure, make sure you do tests or exams or homeworks by a certain period of time, right? There will be regular class time, class meetings, and things like that, like what we're doing today. It'll just be held strictly over Zoom. But yeah, I'm sure she'll post lecture notes and things like that. That's kind of the standard. I feel like nowadays, maybe not, maybe it's not the standard in most departments or whatever, but I feel like when I talk to in the chemistry department, typically post her lecture notes beforehand. But is whether or not she records videos like I've been doing, I don't know, and I'll ask her about that. But she can record, like she'll be able to record the Zoom lectures and should be able to post those. I don't know how she'll post them. Maybe she'll use YouTube like me. Otherwise, I know other faculty members have been using like Media Share or something. I forget, there's some other, is it Media Share? That's what's called? Media Flow, thank you. Yeah, I knew something like that, right? So a lot of other faculty members have also been using Media Flow. And so I'm sure she'll, you know, use one of those two things, but it's very easy to record these Zoom lectures, right, as they're going. Okay, so everything was kind of about the comment about posting lectures and things like that. So, so yeah, so I'll talk to her about that again. she's expressed that, you know, she wants to try to make this as seamless for everyone as possible, as I do as well. You know, and so she'll, you know, so I'm sure she'll try to do things as close to how I do them as possible. So, so I'll talk to her about kind of some of these things when I talk to her tomorrow. Okay, and I can answer some more of those questions on Friday. But any other questions or things? Because again, these are also giving me things to make sure I kind of, you know, mention to her and talk to her when I talk to her. So if you have other thoughts or questions, I'm happy to, you know, yeah. I would imagine so, because again, I think the idea is to not all of a sudden be like, all right, you know, we're 3 weeks in or whatever, let's completely change how everything is being done, right? I don't think she's planning on doing that, through my discussions with her. So I expect it to be the same thing. And I have, you know, all the homeworks, you know, prepared and things like that for the entire semester. So she might just use those completely. Maybe she'll, you know, modify them. Well, I don't know. You know, but yeah, so, but again, I'll talk to her more about those things tomorrow and let you know specifically on Friday. But if there are any other major changes to expect, but again, through what communication I've had so far with her, it sounds like she's trying to minimize changes as best as possible. So, other questions, comments, thoughts? All right. So yeah, so let's kind of get started talking more about the steady state approximation again. So right, we talked about this. We did this example with N205, right, as best as we could without the Zoom and everything. We talked about this mechanism. Yeah, I think we talked about this, right? I think it was the sign was off for something. Was B wrong? Huh? Or something like that. Yeah, I forget. Maybe we didn't do this question. I guess. Oh, okay, we didn't do this question. All right, yeah. I mean, I have like multiple of these questions with slightly different mechanisms and things like that, right? So, so yeah, so you know, here we have this proposed mechanism. There's two elementary steps, if you will. One of them is an equilibrium step, so there's the forward and the reverse. Okay, and then the question is, which of the following is or are incorrect for the above mechanisms? A wrong, B wrong, C wrong, D wrong, or all of them correct, or more than two of them are incorrect. So B here, some people saying incorrect. Any other thoughts? So, right, A, okay, A, NOs appearing only in 2 of the reactions, so it should only have 2 terms, which it has, right? The first term, it's the reactant, so it should be negative. The second term, it's a product, so it should be positive, right? And then those factors of 2 should be there, right? Because of the stoichiometric coefficient of 2 in the chemical reaction it's involved in, right? That its rate of appearance or disappearance is twice as fast as the rate of that reaction based off that stoichiometric coefficient of 2, right? And so A here is correct, right? It's minus 2 K1 NO2 squared, right? Is the K1 NO2 squared is the rate law for the forward reaction, and then there's the factor of minus 2 because the stoichiometric coefficient of 2 and it's a reactant, right? And then 2 K minus 1 NO2 is also correct. B here, N2O2, okay? It's a product in the first reaction, K1 NO2 squared, that's fine. Again, it has a stoichiometric coefficient of 1, so all of these should have a 1 in front, which they do. And then it's a reactant in the reverse reaction and the reactant in the second reaction here. And so those terms are actually fine as well. O2, it's a reactant in the second reaction. And so K2, N2O2, O2 is fine. D here, it's a product. Okay, K2, N2O2, O2 is fine, but it has a stoichiometric coefficient of 2. And so 2 of the, right, so the rate of formation of NO2 is twice as fast as the rate of that reaction, which again, K2, N2O2, O2 is the rate law for that second reaction, which is equal to the rate of the reaction, and the rate, and again, the rate of formation of NO2 is twice the rate of the reaction. So D here is incorrect. Question?
In the book, it was saying like for mechanism one where you have the coefficient of 2, it said like in general you can make the assumption that the coefficient will tell you about the order of that like reactant, but it said it's not like always true. Like do you just make that assumption usually when you're doing that? Does it have to be like experimentally determined to be able to?
So for a general, I don't like that statement for a general reaction, because for a general reaction, the stoichiometric coefficients and things like that don't necessarily mean anything for the overall rate law and the reaction mechanism, the order with respect to those reactants. In elementary steps, the coefficient definitely tells you the order, right? So for elementary reactions, right, where this reaction is talking about NO interacting with another NO to form N2O2, right? That for that reaction, okay, right, that it's definitely second order with respect to NO, because for the reaction to take place, both NOs have to collide to have the reaction occur, right?
So it's true for the elementary reactions, but not for like you just see a reaction.
Yeah, like if I wrote the reaction 2NO plus O2 forming 2NO2, that overall chemical reaction, I don't know if it's second order with respect to NO2 and first order with respect to O2. You know, I'd end up being a little surprised if it was, because that would almost imply like all 3 things have to collide at the same time for the reaction to occur and blah, 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 right? And so it's, you know, not necessarily likely. And we can actually, I guess, why don't we, this is different from this, right? Yeah. So, and I don't have that here. So why don't we go through and see what the actual, assuming steady state approximation, let's see what the actual rate law for this would look like, okay, given the reaction here. Okay. So I'm just writing this out. Okay, K1, K minus 1. And I'm doing this because I want to make sure we do plenty of examples of this stuff, because you know, we'll see plenty of it. Two, okay, right. So let me flip over here, right. There it is. All right, right. So that's our mechanism, right? The overall chemical reaction, right, it is 2NO plus O2 going to 2NO2, right? That's the overall chemical reaction, right? Our intermediate is N2O2, right? So if I assume steady, I'm just going to put SS, the steady state approximation, right? Then that's saying that dN2O2 dt equals 0, right? The steady state approximation for this mechanism is, for any mechanism, right, is that the change in concentration of the intermediate with respect to time is equal to 0. Here we have one intermediate, so it's just saying dNO2 dt is equal to 0, right? So I know, say, for this mechanism, right, I have no idea which is fast, which is slow, blah, 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 right? I'm not making any of those assumptions, right? But I can say, right, that the rate for this overall reaction here, right, the rate of the overall reaction is going to be related, let's say, with minus dO2 dt, right? It's also related with, positive 1/2 dNO2 dt, or minus 1/2 dNO dt, right? The rate of the reaction is related with the rate of changes of the reactants and products in those reactions multiplied by their stoichiometric coefficients, or it's not multiplied, sorry, divided by their stoichiometric coefficients, right? So this is true in general for the overall reaction, okay? So if I want to get the rate law for the reaction, right, what I want to do is I want to find out, I want to pick one of these things, right, and solve for what dO2 dt is in terms of concentrations and rate constants, or maybe I want to do it for NO2 or NO, right? So I can pick any of these three things and you will get the same answer no matter which thing you pick. I promise you that. It will not change your answer, okay? If I'm trying to do this, again, the question is what's the rate law for this overall chemical reaction 2NO plus O2 going to 2NO2 using the steady state approximation, right? And so I can pick to find the rate law, right? Because the rate law is the rate of the reaction equals rate constants times concentrations, right? That's a rate law, okay? So if I want to find that rate law, I need to pick, right, one of these change in concentrations to solve for, okay? I'm going to pick, for example, O2 here, right? I could pick O2, or I could pick NO2, or again, I could pick NO. I don't like the idea of picking NO because it appears in two reactions, so it itself, right, it has more stuff, right? But I can say the rate of the reaction, right, is related with the negative dO2 dt, right, which the rate of formation, right, so negative dO2 dt, right, which, right, dO2 dt, right, if we were to write out what that is, right, so minus sign, so dO2 dt, right, well, O2 in the mechanism only appears in the second reaction, right, as we showed in the slide, right, it's just minus K2 N2O2 O2, right? That was what dO2 dt equals. Right, if we go back, let me autofocus here. That's a little bit better. Now that autofocus, let me go back to the slide just to remind myself, right? Right, dO2 dt is just minus K2 N2O2 times O2, right? And so the rate of my reaction, right, is just equal to negative of that, right? So I'd say, okay, the rate of the reaction is just K2 N2O2 O2, right? And it's, hey, my rate law, I'm done, right? I can't quite do that because why? Yeah, exactly. N2O2 is an intermediate, so I can't just stop here. You do not want to leave intermediates in your final rate law expression, right? So I can't say, oh, this is my rate law, because N2O2 is an intermediate. So I got to get rid of it, and that's where that steady state approximation comes in, okay? And so, right, the steady state approximation, right, is related with dN2O2 dt. Let's zoom out a little bit more, so maybe we'll try refocusing just to make sure we can see everything. right? And so d N2O2 dt, right? Again, it appears in all three reactions, so it's going to have three terms, right? In the first term, it's formed in the first reaction, K1 and O squared, okay? So it's going to be a positive sign, then minus K minus 1 and 2 O2, and then minus K2 O2 and 2 O2, okay? Right? Again, it's the V1, right, minus V, negative 1, minus V2, right, and then those rate laws for the rates of the three different reactions, plugging those in, right? So questions so far about how I got, what I got, where I got, why I got there? Yep.
Wanted to ask about you had referenced the previous slide to put a line or two in there. On that slide, the one that was wrong, I was just kind of a little fuzzy as to what changed. It was
Okay.
probably just a coefficient, right?
Yeah, so what was wrong was right here, dNO2 dt should equal 2K2 and 2O2 times O2 because of the coefficient of 2 there. Yep, exactly. Yep. Any other questions? What we're doing so far, right? And so, right, all this just equals 0, right? That's what the steady state approximation is saying. So we can solve for the concentration of N2O2 in terms of the concentration of O2 and NO, right? Those are my reactants, okay? And so when you do that, okay, what we can do is we can do K1 NO squared minus N2O2 times K minus 1 plus K2O2, right? Solve for N2O2, we just add it to the other side of this equation and then divide by K1, take K minus 1 plus K2O2, right, to get that the concentration of N2O2 equals K1 NO squared over K minus 1 plus K2O2, okay? Right? And so then I can finally plug this back into my rate law above, right? To get that the rate of the reaction, my rate law is equal to K2, K1, NO squared times O2 divided by K minus 1 plus K2 O2, right? And so this is the overall rate of my reaction, okay, which is so roughly, it's second order respect to NO2. It ends up being, right, in terms of its order with respect to O2, right, it depends. For low concentrations of O2, then it's first order with respect to O2, but for high concentrations of O2, then it's going to be zeroth order with respect to O2, right? Right, depending on whether or not K minus 1 is much greater than K2O2 or K minus 1 is much smaller than K2O2 will kind of change the rate law's dependence on the concentration of O2, okay? Right? But that would be the final rate law for this mechanism, which again, if this is your proposed mechanism, this is the rate law you derive, right? Then you can do things in lab to see, does this make sense, right? In lab, I can try to measure what is the order with respect to NO2, right? And see if that's second order. And then, right, for O2, I can see what the order is with respect to O2 for low concentrations of O2 and high concentrations of O2, right? And if I find that it's first order for low concentrations and zeroth order for high concentrations, right? Then that is going to give me, the fact that then that's going to tell me that this mechanism and this proposed rate law seems to be pretty accurate at predicting the reaction, right? And again, that sort of helps, support your hypothesis of this is my reaction mechanism, but there's no way to prove that this mechanism is the mechanism, right? You can just, find as much data as you can to kind of support that until someone comes along to find something that disproves it, or maybe proposes another mechanism that helps explain things even better, But, so questions about this example here? All right. All right, so let's have another wonderful example of the overall reaction to F2O going to F2 plus O2, right, has this following mechanism. And the question is what is the rate law for this overall chemical reaction using the steady state approximation? So I'm going to wait just a little bit of time here so you guys can work on things. If you don't want to kind of work on solving for everything, that's fine. But if you want to do some of the initial steps of writing out what would you find, the rate of the reaction is related with some rate of change, and that's related with these concentrations and things like that. And then what are the steady state approximations equal to and stuff, right? Writing out some of that stuff, if you want to at least get to that far, I think that's very good to do on your own. All right, let's start talking about this together. All right. So, all right, to start with, right, if we're trying to get the rate law, and first start saying, okay, well, the rate of the reaction is going to be related with the rate of change of O2 with respect to time, right? If you kind of add everything up, right, in the overall chemical reaction that was given, right, one of the products was just O2. I think it had a stoichiometric coefficient of 1. So I should have written that down before changing it. But so the rate of the reaction is just related with that, right? And based off of that, right, O2, and one of the reasons why I picked O2 is, hey, O2 only appears in one reaction, right? So that makes life a little bit easier, right? So then I can just write this as Kc concentration of OF squared, right? Now, I guess before this step, we could have said, well, what are my intermediates, right? And so what are going to be the intermediates in this reaction? OF, right? What else? F. Yeah, F2O will end up being one of the reactants, right? So, I mean, it's a lot easier to see. I had on the slides, I should have done this before, right? There's the overall chemical reactions here, right? So we know what the reactants are in the products given the overall chemical reaction, right? And then F and OF are mainly things that don't appear in those, right? So, yeah, so it's F and OF, right? So our steady state approximation, right, is going to say that DOF dt equals 0, right, and df dt equals 0, right? But the fact that OF is an intermediate means I can't use this as my final rate law, right? I got to get rid of that OF in terms of F2O and O2 and what's it, F2, right? It's one of the products, right? Okay. And so let's write out what the steady state approximations are, okay? So we'll start with F here, so df dt. I'm going to first write this out in terms of just kind of rates and things like that. So F appears in how many reactions? All 4, right? F appears in all 4 reactions, right, per rate. So, right, it's a product in reaction 1, or VA, I guess I'll stick with the A, B, C, D listed here, right? So it's a product in the first reaction, right? It's a reactant in the second one, it's going to be minus VB. In the third reaction, it's a product, but there's 2 of them that are appearing, okay? So it's 2 times VC, right? The rate of that third reaction here, because I formed 2 Fs. And then similarly, I'm consuming 2 Fs in that other reaction, so minus 2 VD, right? And all of that's going to equal 0. Okay, and I haven't plugged in right for what those are, but just kind of writing it out like this first, right? And then DOF dt, right? OF itself appears in the first reaction, appears in the second one, appears in the third, but does not appear in the fourth, right? So in the first reaction, OF is a product, so it's just, again, VA. In the second reaction, OF is also a product, so it's just plus VB, okay? In the third reaction, OF is a reactant. That's going to be minus 2 VC, okay, because it's 2 of them are reacting together, so minus 2 VC, okay, and that's it, right? And that equals 0, okay? Right? Right? And so now I have these 2 equations and 2 unknowns, right? And let's see here. So what I'm going to do is on a separate piece of paper, real quick, I'm going to write out what is VA, VB, VC, and VD, right? So VA, right, is just going to be KA times concentration of F2O squared. VB is KB, concentration of F2O. Okay. VC is KC, concentration of OF squared, and VD is KD, concentration of F squared, concentration of F2O. Okay. So really, VA is the only one here that doesn't have intermediates appearing in the rate law, right? Sadly, right? All the other ones got intermediates except for VA. Okay. And so, right, so I kind of did that so we can kind of not worry about those reactions, right? And so, you know, so one of the reasons why I also write things like this is, you know, ignore kind of that stuff right there, right? I have these two kind of equations. I have VA minus VB plus 2VC minus 2VD equals 0, and VA plus VB minus 2VC equals 0, right? Well, one thing I can notice, and, you know, who knows if this is helpful, right? But if I were to add these two equations together, right? Again, add those two equations together, you get two VAs, but the VBs will cancel and the VCs will cancel, right? And so then if I add those together, I see the fact that 2VA minus 2VD equals 0, right? Which if I plug in then, right, for VA, this, so, right, the 2's will cancel, right? So it's just KA F2O squared minus VD here is KD F2 F2O, right? That equals 0, okay? And so, right, from that, okay, so if KA F2O squared minus KD F squared F2O equals 0, right? I can divide out one of the F2Os, right? So at 1, cancel that out, right? And then I can solve for F, right? So F, concentration of F is going to equal Ka F2O divided by Kd, all to the 1/2 power. Okay. Question?
Why would you sum the two rates versus like setting them equal to each other?
I mean, so I could have set them equal to each other. The things would have canceled in the same way or something like that.
I just know if you set them equal to each other, you would get rid of your VA and
Oh yeah, setting them equal to each other would be like subtracting, right? So I could add them together to get this equation, right? If I subtract those two equations from each other, okay, which is essentially what setting them equal to each other would be doing. So if I, instead of adding them, I subtract them. So let me do that here. All right, so if I subtract them, right, so instead of adding, if I subtract, okay, right, then the VAs cancel, and then I'm left with, say, minus 2 VB, and then if I'm subtracting, it would be plus 4 VC, and then, what would that be? I guess so minus 2 VD equals 0. So I could subtract them, and I'd get, say, this kind of equation here, right? And the VAs would go away. So I added them together instead of setting them equal to each other, subtracting them, mainly just because it got rid of 2 of the terms, and I was just left with VA and VD. Again, this is just going through, so how I'm solving this right now is also different than what you'll see on the lecture slide. So if you have the lecture slides printed out, you'll see I did things completely differently than, say, how I'm doing them right now. And part of that is just because I solved the things on the lecture slides a long time ago, and I forget exactly what I did then, right? I mean, you know, also the other thing is just to show that there's different ways you can do this, right? Like once we did kind of this setup here, right? Once we kind of did this setup here, right? Writing out the steady state approximation, writing out the rate of the reaction, right? And everything, right? Once I've set all this stuff up, then it's just mainly algebra to solve, right? I have two equations and two unknowns, right? My unknowns are OF and F, right? I got to solve for the concentration of OF and F in terms of F2O and O2 and F2, right? So those are my two unknowns, and I have two equations. So it's just algebra, right? It's just two equations, two unknowns, solve for X and Y, right? X is OF, Y is F, right? And so however you want to go about solving for X and Y, you know, for your unknowns is up to you, right? Whatever makes more sense to you, right? When you're doing this on homework or on an exam, right? Whatever makes more sense to how you're solving these things, go for it, right? You know, I have done in two different ways, right? In this, you know, what we're doing right now, I'm kind of, you know, doing things to where I write out things in terms of the rate of the reactions and plug in for the rate laws at the very end to try to make things hopefully a little bit more clear. What's on the slides is I write out what these things are with all the concentrations plugged in, and then I go through and solve for variables in terms of other variables and plug things in and whatnot, right? And so there's different ways you can try to go about doing this, okay? But so this is what I got for F, okay? And so then, right, I go back. So now I know what F is in terms of a reactant. So that's great. The problem is my rate law is OF squared. I have no idea what the heck OF squared is, right? So I need to go back here and say, okay, well, let's look at DOF dt, right? Well, that has VA here, which is KA F2O2 squared, VB, which has F and F2O, and then VC, which is OF squared. So if I look at that, I say, okay, well, I know what F is in terms of F2O, and all the rest just depend on F2O. So I can use this equation here, right? So let's plug in kind of for that equation, given this information, right? So DOF dt equals 0, which equals VA, which is KA F2O squared, plus VB, which is KB F2O, and then minus 2 VC, which is minus 2 KCOF squared. Okay. Right. And so I have that, and then I can use the fact that F is equal to KA F2O divided by KD to the 1/2, right? To do this as
Where does the square go that was on the K2O? The K2O or the F2O, sorry.
F2O.
For F.
Here?
No, the last step we're on. Where did
Oh, the squared. Oh, because I had an F2O here and an F2O squared, I divided both sides by like F2O. Oh, sorry. And so that got rid of, yeah, one of them. Yep. There. Right. So doing this, right, what I have, and I'll wait the plug-in for F in a minute, right? So I have 0 equals KA F2O squared plus KB F2O, right? And then again, minus 2 KCOF squared, right? And so I can just add this to the other side, right? And get, what I'm going to do is, I'll show you in just a second, KC times OF squared equals 1/2 times Ka F2O squared plus Kb F2O. Okay. Now, why did I do this? You might be asking yourself, well, if I look back up here, right, my rate law for my reaction is KCOF squared, right? I want to get rid of the OF squared, right? Well, I happen to see that KCOF squared equals all this stuff, right? So I don't have to solve, right? I don't want to divide by KC and then take the square root of everything, because then I'm just going to plug that back into here. I'm going to square it all and multiply by KC again, right? So there's no reason to solve for OF itself. If I solve for KCOF squared, right, I can plug that in. So the last thing I'm going to do here in this line, right, is let's just plug in for what F is. Give myself enough space here. Here we go. Right, so if we plug in for F, this is again 1/2 Ka F2O squared plus, and this is going to be Kb times Ka over Kd to the 1/2 times F2O cubed. Oh, no, sorry, the 3/2, not cubed. Okay, so plugging in for F, right? So I took F here and plugged it in down there. Probably should have like a different colored pen, right? But turn on the white, maybe it's better, right? But again, so I took F and I plugged it into here, right? F is Ka over Kd to the 1/2, so that's where Ka divided by Kd to the 1/2 came from. And then I have F2O to the 1/2 times F2O, so that gives me F2O to the 3/2, right? And so then I can finally plug this in to my rate expression to get that the rate of this reaction, or the rate law, is 1/2, or I'll just put Ka, no, how are we going to do this? Yeah, I guess it's just going to have to be, the rate of the reaction is 1/2 times Ka F2O squared plus Kb Ka over Kd to the 1/2 F2O to the 3/2. Okay, so this lovely looking expression is my final rate expression, okay? Which is not really all that lovely, obviously, right? But this would be the final rate law for this reaction, okay? So some of these things that we're doing in class are going to be a lot more complicated mathematically and otherwise than things that you would have to do on an exam, okay? So you know, if all this algebra is something that you're like, hey, you know, really hesitant about, just note that, you know, on exams, the algebra shouldn't be this tricky, okay? You know, I tend to have a lot more complicated examples in class in terms of the math than on exams, okay? So the main thing, again, to take away from this, even if every last step to get to this final answer wasn't, you know, clear to you, right? The main thing to make sure you take away is, again, some of the first steps, right? From the mechanism here, right? What is my rate law? And then what are my steady state approximations, right? And again, you know, you can plug in for these things into the steady state approximations if you want to write it that way, right? I could have written df dt equals Ka F2O squared minus Kb F2O, so on and so forth, like, right? Which is what I had written again on the lecture slides, right? That is how it's written, right? And then I even in the lecture slide had the rate of the reaction related with df to O dt, okay? Right? Right? So I put the rate of the reaction is equal to this, and then I just need to solve for what F was instead of solving for OF, right? So maybe it would have been simpler, right? You know, using this as the rate of the reaction, right? divided by 2. I should have divided that by 2. Did I divide it by 2 by the end? No. I did not. No. I don't even know where I got that. Yeah, I messed up on some factors of 2, it looks like in these slides, so I need to clean that up. But you see, how I did some things in slides is a lot more kind of complicated, right? But basically found, but if starting from this point here, right? If using what we showed that F equaled, right, KA over KD times F2O all to the 1/2, right? You can just plug that into here and then you're done. You never have to solve for what OF is, right? So different ways of doing this, getting to the solutions, you just get to the solutions differently, right? Let me see here. Where's factor 2's messed up on? Okay, OF, I dropped one of the terms, right? Yeah, I'm missing the KA. Yeah, okay. So I actually, I'm gonna have to fix the slides. I'll re-upload those because DOF DT here is missing a term completely. So that's just wrong. Right? Somehow, do I fix that later? Did I notice that and fix it later? I don't know. Because basically, I mean, the answer is almost the same minus this like weird factor of 2 to the 1/4 that popped up. But otherwise, it's KA and so on and so forth. So, yeah, I don't know how I end up making that work out, even though, yeah. But again, you see that, I did things in a much more potential complicated way, somehow in these slides and stuff. But again, writing out this stuff here is kind of some of the most important steps, right? From there, it's just doing some algebra, okay? Right. Oh yeah, one thing I wanted to note here is for df2 dt, right, or df2o dt, right? Notice here that reaction 4 doesn't appear in this expression, right? And the reason is in reaction 4, F2O is essentially almost like a mini catalyst in that one elementary step, right? The concentration of F2O does not change over the course of that 4th reaction. That 4th elementary step does not change the concentration of F2O, so that's why it doesn't appear in that expression for dF2O dt, okay? Right? Now this is a very rare case. You don't typically see things like this, right? Like reaction 1 and reaction 4 here, where you have, right, where you have, F2O as a reactant and a product. Okay, often you don't have the same thing as a reactant and a product in an elementary step. It's not very common, but it is common, and actually we'll see it pop up again in unimolecular reactions that potentially talked about on Friday. But yeah. Okay. So questions about this example? Again, I'll update these slides, fix some of these typos on here. All right. So,
I have a question.
oh yeah.
So in that first reaction, 2F2O went to 1F2O.
Yeah.
So why is the rate double?
Yeah, no, it shouldn't be. It should just be 1. Now, there's some typos here. We can share that screen, right? Right, this is what you're talking about. It should just be 1 there, and then this should have a term for DOF, right? It should also have KAE. F2O squared, right? So that's how this should be written. So yeah. Okay. Yep. So, and then I guess in this previous slide, again, there's some typos here. In this previous slide, the rate law, right, we find it in terms of that, but right, the rate law is going to be V equals minus 1/2 times that, right? And so, right, when I solve for df2o dt, I need to multiply my final answer by minus 1/2 to get the overall rate law. Which, here I just solve for what df2o dt is and not the actual rate law itself. So yeah. Any other questions? Start sharing that screen. All right. So let's talk about the rate determining step in pre-equilibrium approximation. We'll just kind of talk and define them today, and then we'll likely, not likely, but we'll do some more examples of this Friday. Okay. All right. So the rate determining step, okay, is basically just saying, hey, often in chemical reactions, there's some step that's just really slow. Okay. And that very slow step is what's going to determine the speed, the rate of the overall chemical reaction, right? So again, the common example I like to use for this, I think I got from somebody else, is the idea, right, that if you're in a crowded room, right, which I haven't been in a crowded room in a long time, supposedly, right, but pretend, right, there are crowded rooms yet again in life, and you're in some large crowded room and the fire alarm goes off, right, and you want to leave, right? Everyone wants to leave very quickly, right? Well, you all can run quickly to the door, but if the door only fits, say, one person at a time, right, the fastest you're getting out of that room is how fast can you get through that door, not how quickly can you get to the door, right? There's two steps to get out of the room. Get to the door and then get through the door. Well, everyone's going to pile up at the door, right, because everyone gets quickly to the door, but then people have to go slowly through the door because only so many people can fit at a time, right? So getting through that door is your rate determining step, right, in determining how fast you can leave that room, right? And so it's the same thing with chemical reactions, right? There are certain parts of chemical reactions that occur very quickly, right? And then you get a buildup of stuff until, at the slow step, and things proceed through that slow step at whatever rate they do. And so that slow step is determining how fast you go from your reactants to your products, okay? That slow step doesn't have to be the first step, doesn't have to be the last step, right? It can be any step within your mechanism, right? But typically the slowest step in your mechanism is going to be the rate determining step, that the rate of that slow step equals the rate of your reaction, right? So the rate law of your slow step equals the rate law for your reaction, right? So again, in this example, right, the slow step is this first step. There's a big barrier to overcome, right? And so that is the rate determining step. That is the step in which will determine how fast your reaction goes. And then the rest of them, right, don't matter so much, right? Takes 10 minutes to do this first step and then 20 seconds to do the rest, right? Okay, the overall rate of the reaction is 10 minutes, 20 seconds, but whatever. It's basically 10 minutes, right? Is basically the idea, okay? Right? And so, for example, right, if I have this overall chemical reaction with this rate law, and I know the very first step is the slow step, okay, right? And I ask, what is the rate law for this reaction? Well, the rate law for this reaction is the rate law for the slow step of the reaction, right? Which the slow step of the reaction has a rate law of K1 times concentration of B times concentration of F, which B and F are both reactants. And so you're done, right? That is the rate law for the reaction given this mechanism, right? That if this first step is the slow step, my rate law is just K1 times B times F. And that's it. Okay. And I can stop there, obviously, because B and F are reactants in the overall chemical reaction. So, right? But if, say, the third step was the slowest one, right, then the rate law for the third step is K3I times F. Well, I is an intermediate, and so then we got to go through and use like steady state approximation or something else to help solve for the overall rate law because we don't want intermediates in it, right? But if that slow step happens to be the first step's never got any intermediates in it, right? You can't have an intermediate on the first step of the mechanism because intermediates are formed and then consumed, right? So there's never an intermediate in the rate law for the first step. And so if the slow step is your first step, then whatever the rate law is for that slow elementary step is the rate law for your overall chemical reaction, and you're good to go. Okay. All right. So again, the rate law for this reaction is just K1BF. And again, it's because the rate determining step is that first step, and that determines the overall rate of the reaction. So questions about the rate determining step approximation. All right. So the overall reaction is blah here. Which step in the mechanism is the rate determining step? Given the information in that mechanism. Yeah, the second reaction, II, right? So D, step 2, right? Okay, right? Whenever you're told something is slow, right? If you're ever given a mechanism like this and you're given things like fast and slow, well, that slow is telling you that's the rate determining step. That's the slow step. That's your rate determining step. So the overall rate of the reaction is related with the rate of that rate determining step, which is K2 NOBr2 NO. Right? All right. So often, so the rate determining step doesn't also mean you have like this pre-equilibrium approximation. But if you have the pre-equilibrium approximation, that typically is used with the rate determining step. Because the pre-equilibrium approximation basically is stating if you have some mechanism where you have some equilibrium step, and after that equilibrium step is a very slow step, right, compared to the equilibrium thing, right? So if this first reaction is very fast in both directions, and this reaction is very slow, okay, right, then the pre-equilibrium approximation is just stating that basically this first reaction is always in equilibrium, right? The idea is right, that the equilibrium gets established very quickly because it's very fast, and then the slow step is so slow that even though you're slowly removing I, the equilibrium reaction just reforms the I and maintains that equilibrium between I and A here, right? That even though the concentration of I might be changing over time, right, the concentration of A is changing accordingly to maintain equilibrium, right? Because the equilibrium gets established so quickly compared to how fast the concentration of I is removed, okay? And so again, this pre-equilibrium approximation works only kind of with these rate determining step type approximations because you have to have some slow step after your equilibrium step, right? If K2 is very fast, right, and is equal speed or faster than the equilibrium reaction, then my equilibrium reaction is not going to be able to establish equilibrium because every time it forms I is getting removed too quickly in order to maintain and reach equilibrium, right? And so given, say, this mechanism A plus A going to I, then I going to P, right? And I'm going to use this pre-equilibrium approximation, right? Given the fact that the second step is the slow step, so that's my rate determining step. So the rate of my reaction, right, is related with K2 times I, okay? And then the pre-equilibrium approximation, again, just states that this first reaction is at equilibrium, which means the equilibrium constant holds true. Equilibrium constant for that first reaction, capital K, happens to equal the ratio of K1 to K minus 1, but it also equals the ratio of the concentrations of I divided by A squared, right? And so I can use this relationship to solve for the concentration of I in terms of concentration of A to get the rate law, right? Which again, the rate law is related with dP dt, right? Okay, so I can use this, plug it back into this equation up here, right, to get that the rate of the rate law for this reaction is just K2, K1 divided by K minus 1 times A squared. Okay. So this pre-equilibrium approximation, often the rate laws that you get out of this stuff is a lot simpler, a lot easier than what you get from the steady state approximation. Okay. And we'll see some examples, maybe not today, but see some examples of kind of when using the pre-equilibrium approximation versus steady state approximation, what is the difference in the rate laws that you get? And we'll kind of see kind of right, how you can get the pre-equilibrium approximation from the steady state approximation and so on, right? So yeah, so this pre-equilibrium approximation typically requires a little bit more approximations, if you will, than the steady state does. Okay. Right, because it requires more things to go on. You have to have an equilibrium reaction. The equilibrium reaction has to be fast, and then the next reaction after the equilibrium has to be slow, right? So you got more things kind of required to occur for the pre-equilibrium approximation to work than you do the steady state. Okay. Right, so given the following proposed mechanism here, what is the overall rate law that is consistent with using the pre-equilibrium approximation? Oh shoot! In every one of these expressions, I put BR instead of BR2. Don't be like, it's supposed to be NOBR minus K minus 1 NOBR2, right? It's supposed to be BR2, not BR. So haha, it's E, right? No, don't pick E because you see BR instead of BR2. That should be BR2 in every last one of those things. That's just me having a typo here. Anyone have any suggestions? What they think the answer is? I just got a favorite multiple choice answer. A, B, C, or D. C's, B's. So the correct answer here is, in fact, going to be C. Right? So how do we get that? Well, right, the rate of this reaction, right, again, the rate of reaction based off kind of that slow step, K2, and O, and I know you can't see this, I'll flip over in just a second, BR2, and O, and then okay. So, right, basically for this, right, the rate of my reaction is equal to this, right? This is my slow step. So K2, NOBR2, NO is the rate of my reaction. Well, that's an intermediate. My pre-equilibrium approximation says that the first reaction is at equilibrium, which equilibrium constant is the concentration of the products over reactants, right? Raised their stoichiometric coefficients, okay, which happens to equal K1 over K minus 1. Again, the equilibrium constant K is the forward rate constant over the reverse rate constant, okay? So it's K1 over K minus 1. equals that, right? And so then basically you just multiply NOBR2 to this other side, NO times BR2 to this other side, and then plug that into here to get the K1, K2 over K minus 1 times NO squared times BR2. Okay. Questions about that? Okay, so again, that's C here is the answer. Yeah. Yeah. So going back to the sheet here. Yeah, and so how you kind of get to this, so if you remember when we talked about equilibrium, I mean, this was a couple of lectures ago, we talked about equilibrium reactions and elementary reactions, right? If a reaction is in equilibrium, right, that means the forward rate equals the reverse rate, right? Well, the forward rate is, you know, say V1, the reverse rate is V minus 1, right? So V1, this is K1 and O, BR2 equals, I did not give myself enough room here, but K minus 1 and OBR2, right? So these two things equal each other. And so if I divide NOBR2 onto the other side and divide K minus 1 onto the other side, I get this ratio here. And then I note, hey, this ratio of NOBR2 divided by NO times BR2, that happens to be the same thing as my equilibrium constant. And so, yeah. So you are correct that K1 and NO and BR2 have to be like together, but they're multiplied together, right? So I need to multiply this onto the other side to get K1 NO BR2, right? And vice versa. So, yeah. Good question. All right. And just a note, if you did the steady state approximation, I'm pretty sure D is the answer you'd get. Let's see here.
Yeah, what was wrong with D, if you don't mind?
D is the steady state approximation. I'm pretty positive. That and then yeah. So D is what you'd get from the steady state approximation, not the pre-equilibrium, right? Which basically the steady state approximation, right, is saying that K minus 1 is the pre-equilibrium approximation is saying that this step is very slow, which means K2 is very small and K minus 1's got to be very large because it's fast. And so it's saying K minus 1 is much greater than K2 times NO. And so that goes away, and then you're left with the pre-equilibrium approximation. So, so the pre-equilibrium approximation, again, you can get from the steady state approximation if you apply it later. But yeah, so D is the steady state, not the pre-equilibrium.
So knowing between those two answers is kind of half the battle. Like if you see them both, you know, like that. Because I mean, you know, it's convenient patterns, right? Like there's things in that steady state that appear in the overall rate, right?
Yeah, I mean, so
they're comparables. Right?
Yeah, they are. I mean, in mechanisms like this, where there's two kind of steps, one's in equilibrium and one's not, things like that. You know, this type of comparison in their form it is common, but you know, if the mechanism is a lot more complicated and there's more steps and things like that, then it becomes more and more difficult to really kind of compare the two and be able to see a trend between them. So I would say, you know, in general, I wouldn't necessarily try to look for trends in final rate law expressions based off of steady state versus pre-equilibrium, just because, yeah, it really kind of depends on the mechanism, right? But I mean, you know, like for this type of mechanism, if I replace these molecules with different molecules and things like that, right, I'll get the same general form. Will be, you know, a ratio of rate constants times, you know, concentrations of the reactants and you know, and some complicated denominator for the steady state versus pre-equilibrium. But yeah, it very much depends on the mechanism and things like that, and so it's difficult to find trends. All right, so I think we'll kind of have to kind of stop here. And next time we'll go over some more examples. So I have this example where we'll do this simple mechanism with a steady state and the pre-equilibrium to kind of show the two and how they compare. And then we'll also talk about unimolecular reactions and such on Friday as well. Okay. Yeah, otherwise I will see you guys on Friday. And don't forget, right, if you're online, submit your homework online in class and hand in your homework if you haven't done so already in front of us.